In this example, we're going to look at the area of a surface of revolution. Here we have the formula that we're going to be using, and it states that if we let f of x be a function greater than or equal to 0, and if its first derivative is continuous, then the surface area of a revolution is given by this formula. And you can think about the formula as being 2 pi r. So 2 pi r times ds, where f of x is rotated about the x-axis. And we are going to say that x is between a and b. And we have this first example. So we have the equation y equal to the square root of 1 plus e to the x, as x goes from 0 to 1, and we're going to be rotating about the x-axis. So the first thing I would like for us to do is to look at the graph. So here I have a portion of the graph. So we have f of x there, where f of x is equal to the square root of 1 plus e to the x. And what we want to do is we want to look at the x values from 0 to 1 inclusive. So that means that we want to look at this part here. And we want to rotate that length of the curve about the x-axis. So we're going to get the length, not the area. Got to be careful. We talked about area in the past. We're only getting that curve, and we're going to be rotating it about the x-axis. So when we get this portion of the graph and we rotate about the x-axis, you get something that looks like this. Actually, I'll start drawing a portion of it. So we're going to have this point here, and we're going to be rotating it. So let's say we have something that looks like this. And then we're going to get this portion here, or this point here, and again, we're going to be rotating it. So what we're essentially doing is we are getting this graph here, and we're rotating it about the x-axis. So getting the graph and rotating it. Okay. Again, we're only rotating that length of the curve. So when you rotate, you get something that looks like this. We're only looking at the surface, okay? So please be careful. We're only looking at the surface. Let me do this in color. We're only looking at the outside, okay? So what we want to do is we can think about getting the circumference of each of these circles. So we have 2 pi r, where r is the distance from the axis of revolution to the curve. And the distance from the axis of revolution to the curve is going to be equal to y. And that's what we have in our formula, f of x. So we're going to get this circumference, and then we're going to multiply times the height. Well, the height of it, you can think about it as being the length of the curve, which we're going to write as a ds. And we talked about the integral from a to b of ds in the past. So let's go back to doing the problem. We can say that the surface area of this revolution is equal to the integral from 0 to 1 of 2 pi times, again, the radius or the distance from the axis of revolution to that curve, which is nothing other than y. But what is y? Well, y is equal to the square root of 1 plus e to the x. So I'm going to write it down as the square root of 1 plus e to the x ds, where ds is equal to the square root of 1 plus f prime of x to the second power dx. So the surface area, one more time, is going to be equal to 2 pi, the integral from 0 to 1, the square root of 1 plus e to the x, times the square root of 1 plus f prime of x squared dx. We know, let's do a little bit of algebra. We know that f of x is equal to 1 plus e to the x to the 1/2 power. So f prime of x is going to be equal to 1/2, 1 plus e to the x to the negative 1/2, times the derivative of the inside, which is e to the x. So we can say that f prime of x is equal to e to the x over 2 times the square root of 1 plus e to the x. And now we're going to square f prime of x because the formula requires it. So f prime of x to the second power is equal to, I'm going to show the work up here. We're going to square both sides. So this is going to be equal to e to the 2x over 4 times 1 plus e to the x. We're squaring the numerator and we're squaring the denominator. The next thing that we're going to be working on is adding 1 to that previous step. So 1 plus f prime of x squared is equal to 1 plus e to the 2x over 4, 1 plus e to the x. We know that in order to add fractions, we need an LCD. So we're going to have 4 times 1 plus e to the x plus e to the 2x over 4, 1 plus e to the x. So I multiply both numerator and denominator in this fraction by our LCD. And then that gives us this in the numerator over the denominator. But then I combined the fractions into one. Plus 4 factors out into e to the x plus 2 squared over the denominator, which is equal to 4 times 1 plus e to the x in the denominator, dx. All right, so let's simplify a couple of things. The square root of 4 is 2 in the denominator, and that 2 will simplify with the 2 outside of the integral. And then one more time, the square root the square root of the denominator will simplify with the square root out here. And then last thing, the square root and the square will simplify. So our answer is going to be s is equal to pi, the integral from 0 to 1 of e to the x plus 2 dx. So let's integrate and see where that takes us. We have pi times e to the x plus 2x, and we're going to evaluate that from 0 to 1, which gives us pi times e to the first plus 2 minus e to the 0, which is 1, plus 0. So our final answer becomes pi times e plus 1. So the area, the surface area of this revolution is equal to, so the area, and that is surface area, we're using S to represent the surface area. S is equal to pi times E plus 1, we said. I'll attempt to do another example right now. Let's say we have another problem, and in this problem, we want to find the exact area of the surface obtained by rotating this curve about the y-axis, where y is from 0 to 1. So we're going to be rotating about the y-axis, but we're only going to be rotating the part of the curve, not the area, again, the part of the curve that goes in terms of y from 0 to 1. So we're looking at rotating this part about the y-axis. So when you rotate about the y-axis, you're going to have the surface area generated. Let me see if we can do this. So we're only looking at the outside, right? The surface area. So if we look at how it's going to look, you're going to have something like this. So I can kind of see, I'm not sure if you're looking at it, but you can look at it as a cone, like an ice cream cone. Think about a waffle cone. So we're looking at just the waffle part, right? A waffle cone, an ice cream cone. So if you were looking at the volume, then you would be looking at the ice cream inside of that cone. All right, so I'll leave it here. So what we want to do is we want to look at the formula and see where that takes us. So we know that the surface area is going to be equal to the integral from C to D now, because we're integrating with respect to y. So the surface area is going to be equal to the integral from 0 to 1. And then we're going to have 2 pi. Now, remember, the formula that I wrote first said y. I'll bring it up here. The formula that I said first said y, or f of x. But in this formula, we were rotating about, this is rotated, about the x-axis. So here we're rotating about the y-axis. So that's why I like to think about it in terms of the radius. So what is the radius? Well, the radius is equal to the distance from the axis of revolution to the curve, right? So I'm going to write it down as, let me say x, but remember, we're not going to be integrating with respect to x. What is x? X is equal to a function g in terms of y. So we can say that the radius is just the distance from the axis of revolution to the curve, which in this case is just the curve, g of y times ds, which we say this is equal to 2 pi, the integral from 0 to 1, g of y times the square root of 1 plus g prime of y squared dy. So this part here is your ds. Okay. Let's figure out what is g of y. Okay. There's a lot of algebra here. Okay. So please be very careful. What is our g of y? Let's solve for x. We know that x to the 2/3 plus y to the 2/3 is equal to 1. So x to the 2/3 is equal to 1 minus y to the 2/3. Or x is equal to 1 minus y to the 2/3 to the power 3 over 2. Because what I'm doing is I'm multiplying or raising to the power 3 over 2, so that when you multiply it becomes 1. So we're raising to the power 3 over 2, and that's why we get that. So we can say that g of y is equal to this portion right here. The formula that we just talked about had a g of y, and it's also going to have a g prime of y. So why don't we do that now? Why don't we get a g prime of y since we're here? We can say that g prime of y is equal to 3 over 2 times 1 minus y to the 2/3 to the 1/2 times the derivative of the inside. And the derivative of the inside will be equal to a negative 2/3 y to the negative 1/3, right? It's negative because this part here is negative. And then you're applying the derivative to y to the 2/3. Let me simplify that a little bit. We're going to have, let's look at this. The 2 and the 2 will simplify. The 3 and the 3 will simplify. And we can say that g prime is equal to, I'm going to write it down in the form of the square root of 1 minus y to the 2/3 over y to the 1/3. And then don't forget we have a negative there. Our formula is going to require us now to square this derivative. So we can say that g prime of y squared is equal to 1 minus y to the 2/3 over y to the 2/3. Okay, so remember we are squaring both sides of the equal sign. All right, so after we square, the formula is asking us to add a 1. So if we say 1 plus g prime of y squared, then all we're doing is adding 1, right? But when you're adding 1, you know you have to get the LCD. So we can say that this is going to be equal to y to the 2/3 plus 1 minus y to the 2/3 over y to the 2/3. And we can simplify this a little bit more. This is going to be equal to, we can simplify the positive y to the 2/3 with the negative y to the 2/3. And then we are left with 1 over y to the 2/3. So now I'm going to get this information and plug it in. 1 over y to the 2/3. So this is going to be equal to 2 pi, the integral from 0 to 1. What was g of y? G of y is equal to 1 minus y to the 2/3 to the 3 over 2, remember? times the square root of 1 over y to the 2/3 dy. So 1 over y to the 2/3. This is going to be equal to 2 pi, the integral from 0 to 1 minus y to the 2/3 to the 3 over 2. And then if we simplify the square root, then we're going to have over y to the 1/3. I just want to show you 1 over y to the 2/3 to the 1/2. This is this part here. So this is radical 1 over y to the 2/3 times 1 over 2, which simplifies your 2, and you're left with 1/3. We have dy. Looks a little complicated, but what we can do is we can apply substitution. Why don't we let u be equal to 1 minus y to the 2 over 3? And our du is going to be equal to negative 2/3 y to the negative 1/3 dy, which is equal to negative 2 over 3 in your denominator y to the 1/3 dy is equal to du. So I'm going to just isolate 1 over y to the 1/3 dy, and we can say that negative 3 over 2 du is equal to 1 over y to the 1/3 dy. So all that I did there is I multiplied both numerator and denominator by a negative 3 over 2. That is, I multiplied both sides by a negative 3 over 2. So it simplifies, and then you're moving it over to the other side. All right, so let's see where this takes us then. With this in mind, we're going to say that the surface area is equal to 2 pi. The integral from, now we made substitutions, right? So instead of going from 0 to 1, when you let y be equal to 0, u is equal to 1. And when you let y be equal to 1, u is going to be equal to 0. So we have 2 pi, the integral from 1 to 0 of, let's see here, 1 minus y to the 3 over 2 is equal to u. So we can say that this is going to be u to the 3 over 2 negative 3 over 2 du. Let me clean that up a little bit. So the surface area of this revolution is equal to, we can simplify the 2. I'm going to factor out that negative 3. So we have negative 3 pi, the integral from 1 to 0 of u to the 3 over 2 du. And we don't need to do this next step, but since we're reviewing, I'm going to do it anyway. This is going to be 3 pi, the integral from 0 to 1, u to the 3 over 2 du. And remember, I can do that because we have a negative, and we're changing the limits of integration. And that is changing the order of the limits of integration. So finishing this problem, we have 3 pi times u to the 5 over 2 times 2 over 5. And we're going to evaluate that from 0 to 1. So we have, what is this here, 6 pi over 5 times, at 1, you get 1, and at 0, you get 0. So your answer for the surface area of revolution is going to be 6 pi over 5. It's a very long video, so make sure that you pause, and I'll try to post more videos if I can, but just remember that when you're applying it into the formulas, you got to think about what g of y represents and ds represents. Or think about what, one more time, f of x, what f of x represents and what ds represents. And then the other thing that you need to be careful is when you're rotating, either about the x-axis or about the y-axis. All right, I'll stop right here.